Welcome everybody to Math 70. This video lecture is section 3.1. The title of this section is Solving Systems of Equations by Graphing. So before we talk about solving systems of equations by graphing, we need to talk about what a system of equations is. A system of equations is simply one or more equations involving one or more variables. We've been working with very simple systems of equations, something like 3x plus 2 equals 14, right? That's one or more equation and it has one or more variables. And to solve it, we want to determine, we want to determine what our variables are equal to. In this simple system of equations, our variables are equal to 4. X is equal to 4. However, many times we come across more than one equation in our system, and that equation usually also has more than one variable. So as an example of a system of two equations with two unknowns or two unknown variables, we often use a brace symbol to show that we're working with two or more related ideas. I have x plus y equals 5. That's one of my equations. It's got two variables. And so I might have another variable like x minus y equals 3. Now, if I want to solve this system, I need to find both x and y. One equation is not going to be enough for me to solve that. This equation, well, x could be 0 and y could be 5, but x could be 1 and y could be 4, or x could be 12 and y could be -7. So one equation is not enough to find out two unknown variables. You need at least two equations. Solving a system of equations means finding the values of all the variables that make all the equations true. And let me go back to this original or this example to show you. So if I want to solve this system of equations, I need to find both x and y that make the first equation true and the second equation true at the same time. So let's try a numeric approach. Okay, let's let x equals 0. Well, then if x plus y equals 5, that must mean that y has to equal 5, because 0 plus 5 is 5. But that is not going to work in the second equation when I take x and I subtract y, because 0 minus 5 is not equal to 3. So solving the systems of equations means I need an x and y that make both of them true at the same time. And let's just try, because I made this equation up, I know a good one to try. Let's try x equal to 4. Well, in that case, y must be equal to 1 because 4 plus 1 equals 5. And I'll try that in my next equation, x minus y, 4 minus 1, yes, that equals 3. So my solution to my system of equations is the x and y values that make both equations true at the same time. Now, if you have one that is of this nature, which is technically a pretty simple system of equations, you might be able to figure out numerically by guessing and checking. But most of the time, guessing and checking is going to take a super long time and isn't really worth the effort. So this section is about graphing to solve systems of equations. So let's use those same two equations, x plus y equals 5 and x minus y equals 3. And let's graph both of these equations. This is something we worked on in the last chapter. So let's build our axes. And I talked about how to graph an equation in standard form, a linear equation in standard form, but it might be easier to get both of these into slope-intercept form, because it'll be easier for us to graph. If x plus y equals 5, then that means y equals 5 minus x, or I could write that as y equals negative x plus 5. If I add x to both sides, I get x plus y equals 5. So 1, 2, 3, 4, 5. Negative x plus 5 is this line here. And it keeps going, and it keeps going. This is y equals minus x plus 5. And this line, if you remember before, this line is showing us all combinations of x and y that make the equation true. Well, that's a good start, because any solution to my system had better be on this line. And now let's do our next equation. If x minus y equals 3, then minus y is going to be minus x plus 3, because I subtract x from both sides. And now saying if negative y equals minus x plus 3, that means y equals x minus 3. And so that is a line that looks like this. Y equals x minus 3. And again, any xy combination I pick had better be on this line, or else it's not going to solve this equation. And it just so happens that there's one point that is on both of those lines, and that is the point where xy equals 4 comma 1, which means x equals 4 and y equals 1, and that's exactly the solution I found using guess and check. So the takeaway from this example is the solution to a system of equations, at least two equations and two unknowns, because let's see, how about a system of equations in two variables is the intersection of the graph of each equation. The point 4 comma 1 is the intersection of my two lines, and it is the point that satisfies both my first equation and my second equation. Let me do one more by hand, and then I'm going to switch over to Desmos so that things can go a little faster. Because one thing that Desmos is really good at is it's really good at graphing pretty quickly. I wrote my first two or my first system of equations, both in standard form, but it doesn't have to be that way. It could look something like y equals negative 1/2 x plus 6 is my first equation. And let's see. I'm going to come up with the second equation in just a minute here. The other one could be something like 3x equals y plus 1. The variables can be anywhere. They don't all have to be in the same place. But the first step for these is probably make sure they're both in slope-intercept form if you're going to graph it by hand. This top one is. I have the slope of -1/2 and the y-intercept of 6. And the second one, I can get it pretty easily if I just subtract 1 from both sides. Then I'd have 3x minus 1 equals y. And I can just change the order of those two equations. So there we go. Now I'll graph this on a coordinate plane. I have to give myself enough space to get my y-intercepts on there. So I'm going to make it a little off-center. 1, 2, 3, 4, 5. Yeah, just barely made it. There's 6 right there. And every time x moves over 2, y moves down 1. So over 2, down 1, over 2, down 1, over 2, down 1, etc. That's my y equals -1/2 x plus 6. And any solution to this system has to be on this line because it has to solve my first equation. And then my next equation has a y-intercept of -1 and then has a slope of +3. And that's y equals 3x minus 1. And here is my point of intersection, where x is 2 and y is 5. So x equals 2 and y equals 5 is the solution, and it happens to be the only point that solves both the first equation and the second equation. So it's the solution to my system of equations. Okay, I'm going to hop over to Desmos just to speed up the process a little bit and show you how to solve these using Desmos a little more quickly. Okay, here we are in Desmos, and we're going to solve the system of equations -2x minus 8y equals 8 and 8x plus 16y equals 8. So the way you solve this in Desmos is you put the first equation in. We do not have to get this into y-intercept form because Desmos can handle an equation with two unknowns, no problem. Here's my first line, my second. And I can already tell there's going to be a solution because these lines cross each other. And where do they cross each other? Desmos will let you click right on it and give you the point. And that is all it takes to solve equations using graphing. Let me pull that point back up. X equals 24, y equals -7. And so in your homework, you would write this as 24 minus 7 in parentheses. That's how you do it. You write one equation, you write the other, you look for where they cross. Desmos will allow you to click where they cross and show you the coordinates, and that's your answer right there. Let's try another one. I'm not going to write the note first, but I'm going to solve y equals 5/4 x plus 7 and minus 16x, no, minus 6x minus 16y equals 96. And there it is right there. The point where they cross, x is -8, y equals -3. That's the only XY combination that solves both of these equations at the same time. So it's the solution to the system of equations. Now you can have more than two equations and you can have more than two unknowns. And the process for solving them is very similar, but we don't do that in this class. We stick with two equations and two unknowns because that's enough information to practice this process. So far, I hope you've noticed that in each of the systems that I've graphed, the two lines have crossed each other because it's the point where they cross, it's where they intersect that the solution is. But we can also have lines that don't cross each other. Like I could have y equals x plus 1 and also y equals x minus 4. These lines are parallel, which I talked about in a previous video. Parallel lines never cross. Parallel lines never cross. This means that there is no x, y coordinate point or ordered pair that is on both lines at the same time. And this means that there is no solution to the system of equations if the lines are parallel. And that's how we determine if a system of equations doesn't have solutions. And remember, we talked about this way back when we were talking about contradictions and identities and that other one, conditional equations. If you're trying to solve a system of two equations and your lines are parallel, you're never going to find a point that's on both of those lines. So there is no coordinate pair that satisfies both equations at the same time. And so there is no solution. There's no solution to this system of equations. Now, it's pretty easy to see from the formulas that these lines have the same slope because they were both written in slope-intercept form, and the slope was 1 in both cases. But parallel lines never cross. Parallel lines never cross. Even if your equation is not obviously a set of two parallel lines, there's my first one, minus 10x plus 6y equals -30. And here's my second one. As soon as you graph them, you'll be able to see that, yes, those lines are parallel, and therefore there is no solution to this system of equations. This is like our contradiction when we were solving a single equation. When your lines cross, and I can make them cross super easily just by, for example, deleting that. Now they cross. Now there is a single solution. This would be like a conditional equation. The other possibility is you could have two equations that look different, but represent exactly the same line. For example, if I had y equals x plus 1, and then I also had 2y equals x plus 2. Nope. 2y equals 2x plus 2. The equations look different, but one is directly on top of each other. What that means is the coordinate point 0, 1. Not only does it solve the first equation, it also solves the second equation. But so does the point -1, 0. That solves both equations. And so does the point 1, 2. here, that's solving both equations. In fact, there's an infinite set of coordinate points that solves both equations at the same time. So if you have two equations that look different but represent exactly the same line, i.e. the lines coincide, then the solution set has an infinite number of solutions in it. This solution set includes 0, 1, and also -1, 0, and also 0.98, 1.98, and 1.45, 2.45. Every single one of these coordinate pairs is a solution to my system of equations. So I have an infinite, because the lines coincide, there is an infinite set of solutions to this system of equations. And that's how you solve equations by graphing. Most of the time, you're looking for equations that cross at a single point. Every once in a while, you may come across a system of equations that coincide, so you have infinite solutions, or that are parallel, and so you have no solutions. All right, that wraps it up for this video. Our next video will look at solving these systems of equations using symbolic methods, so using hand methods.